Alright, NEET Aspirants, welcome you all to your own beautiful platform Physics Wala. This is your physics teacher Gaurav Tiwari, and today we are going to start off a new chapter in our NEET preparation journey with this awesome new channel PW NEET English. If you observe the environment around you right now, you will find that many aspirants are feeling very high anxiety and very low confidence. And if the same thing is happening with you as well, know that it is absolutely normal, and there are only two things you can do to overcome it. The first thing is conceptual understanding, and the second thing is practice. You have to support your concepts with the practice. I have created these series in such a way that every lecture will cover all the concepts from your NEET perspective, and after the lecture I will give you the DPP in the description section. So just download the DPP after every class and solve it. If you do that gradually, you will find that, my dear aspirants, your anxiety is moving down and your confidence is moving up, and by the time paper arrives, you will find yourself absolutely ready to tackle any problem. Keeping that in our mind, let us start right away with the first chapter of NEET Physics, which is Units and Measurement, and this is going to give you 4 easy marks in the NEET exam. So here it is. These are the topics of this particular chapter, right? We will start right away with the first topic, which is error analysis, right? So let's start right away with the error analysis, right? Let's have a look at that. Now, to talk about the concept of error analysis, we have to divide it into 3 subtopics, which is error of measurement, types of error, and combination of error. We will understand them, each one of them one by one, and our understanding of this section of error analysis will be completed, right? So let us start right away with the first part, which is error of measurement. What is that? Very simple thing. Imagine that we go to the market and buy this stuff, right? The actual length of this object is written behind the box, right? What is the length of the object? But still, you tried a measuring tool, a simple scale, right? And try to measure it, right? So you just place it right next to it and try to take the measurement of this particular thing, right? So what was happening? The actual measured value that was written behind the box, that is the true value, right? The true value of this particular thing, the true value of this thing was something. The true value was written behind the box, and then you measured it as well. So there was some measured value. Now you found out that those values were not same. Let's say the true value was 20 centimeter and the one that you measured was 20.1 centimeter, right? So you can say that the measured value and true value had a little difference, and that difference is called as the error of measurement. So what is error of measurement, my dear students? We can say the difference between the true value and the measured value of a quantity is called as the error of measurement. Simple, right? So depending upon how we use it and the context in which we use these errors, right, there are different types. Let's talk about them. So we have the first type, which is called as absolute error, right? Absolute error, we will talk about it. Then mean absolute error, relative error, and percentage error, right? All 4 of them are related, right? All 4 of them are related, and we can understand them in very easy way. Let's have a look at that, right? Let's have a look at each one of them in step-by-step fashion, right? Okay. So let us first talk about the absolute error. So what is the difference? What is the meaning of absolute error, right? It is the magnitude of the difference between true value and measured value. So try and understand it, right? Again, you go to the market to buy this, right? The true value is, let's say, the true value of the measurement of this particular thing. True value of measurement of this particular object was 20 centimeter, right? So it was written behind the box, okay? And the measured value, the one you measured it, measured value of this thing was, let's say, 19.8, right? Then the difference of these two, right? The difference of these two is going to be how much? The difference of, let's say, the true value is represented by A, and the measured value is, this is the first measured value, let's call it A1, right? So the difference between them is, let's say, delta A, which is A1, A minus A1, but the magnitude we have to take, so it is the magnitude of this difference, which is 20 minus 19.8, which is 0.2, right? Now, right now, you can say that this is the absolute error, right? And the absolute error cannot be negative because every time you are taking the magnitude only. So if you over measure it or under measure it, in both cases, the magnitude is always going to be positive, right? So this is the absolute error, very simple. Let's talk about the next one, which is the mean absolute error. So whenever we talk about the mean of anything, so we are talking about a data set, not an individual data. Imagine that we have the same object, right? We give this object to the entire class, right, for to measure, just to measure it, right? So what happens, every kid takes a different measurement, right? Let's say that the actual value was something, but what is happening, the actual value was 20 centimeter, right? This was the actual value, 20.0 centimeter, right? And let's say that different kids are giving the different values. The first kid has measured it A1. Let's call it A1, the first measurement of the first kid. It is 20 point, let's say 1 centimeter, right? Second kid has measured it and it comes out, let's say the value that he measured was 20.2 centimeter. The third kid measured it and it came out to be 19.9 centimeter. And the fourth kid that measured it is, let's say, 19.8 centimeter, right? So see that all of them were slightly off from the true value. So all of them have made some error in the measurement, right? So in each case, what is going to be the absolute error of each measurement? So let's say that absolute error in the first measurement is going to be a difference of these two, magnitude of difference of these two, true value and the measured value, right? So delta A1, absolute error in the first measurement is going to be 20.1 minus 20, which is 0.1. You only have to take the magnitude, so it is 0.1 centimeter, right? You don't need to take the sign because a magnitude mod is there, right? Again, the absolute error in the second measurement, A2, it is delta A2. What is that? 20.2, actual is 20, right? So difference is 0.2 centimeter, right? Now what is happening? You see that the measured value is lesser than the actual one. Should we go with a negative sign or positive sign? No worries, because absolute error is magnitude of difference between true value and measured value. So magnitude is always positive. So delta A3 is going to be 0.1 only, right? And similarly, delta A4 is going to be difference of these two, 0.2 centimeter, right? So what is mean absolute error now? Whenever we have multiple measurements with each one of them having their own absolute errors, we can take the mean of this absolute error to talk about the like common, the mean error of that data set, right? So there are 4 measurements you took, right? Okay. So if you just add them up, delta A1 plus delta A2, delta A3 and delta A4, right? There are 4 measurements you took, right? So divide them by 4, right? So that will give you the mean absolute error delta AM of this particular data set, right? So here you can say that what is the value? 0.1, 0.2, 0.1, 0.2. Just add them up, it is 0.6, right? Divided by 4. So that is the mean absolute error of this specific situation, right? So in any case, if there are n measurements, right, each one having their own errors, just add them, add all the individual absolute errors and divide by the total number of measurements available in the data set. You will get the mean absolute error of that data set, right? I hope the idea is very, very clear, very simple part. Let's move on and talk about the relative error or fractional error, right? Now, some kids get confused in this one, right? But it is very, very easy, right? Relative error you can have in different situations. Let's say that you have only one data, right? Let's say you are trying to again measure the same object. It is boxed, right? So in this situation, if you have only one data set, you have only single data, only one kid has measured it, okay? And you know the true value in this situation, okay? You know the true value behind the box, it is written, right? So true value of this thing is written, let's say 20 centimeter, right? Okay. And the measured value that is there, let's say one kid is measuring it and it comes out to be 20.1 centimeter, right? So what is going to be the absolute error of this situation? We can say that there is only one kid that is going to measure it. So absolute error in this situation is 0.1 centimeter, right? No problem with that, right? In this situation, the relative error or the fractional error, if you have to write down, what will you do? So in this situation, the fractional error fractional or relative error, how will you write it? Relative error will be, we can say absolute error in this situation related to the true value. So delta A1 upon the true value. So what is delta A1? Over here it is 0.1 and the true value is 20. 0.1 upon 20. That will give you a fractional or relative error in this measurement, right? So what is that? It is absolute value, absolute error upon true value, absolute error upon true value. That is a relative error in this situation when you only have one data. Now it is also possible that you have a data set, just like the previous situation. You have a data set, multiple kids have measured it, and in that situation you have to find the relative error, right? How can you do about that? My dear aspirants, many times what happens, we don't know the actual value. For example, if I have, we don't know, sometimes we don't know the true value of the measurement. Let's say right now we have the box, right? Right now we can read behind it what is the actual length of this thing, but somehow if this box is lost and we only have this, right? So where will you get the true value, right? Where is the true value right now? Multiple kids, different kids are measuring it, but where is the true value? So in that situation, we have to go about a certain way of going about it. So let me tell you how to do that, right? In that situation, when you don't know the true value, it is not given, right, anywhere, right? So how will you go about it? When you have a data set, when you have so many values at your disposal, so in that situation, how will you talk about the thing? So let's say that there are 4 measurements. So what will happen? If you don't know the true value of anything, first of all, you need to calculate the true value first so that you can get the error, right? So whenever you want to know the true value, first of all, you take multiple measurement of something, right? So now understand that I'll measure it, I'll give the scale and this object to the first kid. He'll get the first measurement. What is the first measurement? Let's say it is, again, let's take the same values, 20.1, 20.2, 19.1, 19.9 and 19.8. Let's say that, let's take the same measurements, right? Just to understand this. So these are the 4 values somebody has measured, right? So we don't know the true value. The box we have lost, right? And in this situation, we want to calculate the relative error in this situation. So how will you do that, right? Now let's understand this particular part, right? First of all, our first struggle is we don't know the true value. So in this situation, we take multiple measurements. When we don't know the true value, we take multiple measurements and we take mean of those values. So mean of those values, remember that we are not taking mean of error or anything. We are just taking the mean of the measurements, right? So whatever the measurements, we have taken 4 measurements. So mean of them is going to be A1 plus A2 plus A3 plus A4 upon 4, right? So just add them up and divide by 4, right? That will give you the mean value, right? And this mean value will work as a true value, right? This is the mean value, or it will also work as true value. Got it? Okay. Sometimes you don't know the true value of any object, right? Then what do? You take the multiple measurements and then you take the mean of those measurements, and that mean is going to work as a true value, right? Now you have everything, right? Now you have the true value, right? So what will you do? So in this situation, you will go ahead and then talk about this definition. What is written here? The relative error is measurement of any measurement is defined as the ratio of mean absolute error to the mean value. Mean absolute error to the mean value. What is mean absolute error? In the previous page, I have explained that mean absolute error is summation of all the absolute errors divided by number of data points, right? So here we have 4 observations, 4 measurements. You can calculate the mean absolute error of each one, right? You can calculate the mean absolute error, you can calculate the absolute error of each one. So delta A1 is going to be 0.1, right? 20.1, whatever the difference is, right? Whatever the mean value comes out. So let's say that mean value comes out is 20.0, right? Let's say this is the mean value that you get over here, right? Okay, let's say 20.1 or 20.2, whatever the value comes out. Let's say 20.1 is coming out, right? This is the value that is coming out over here, right? Okay. This is the mean value or true value. Okay. Just put the values and divide by 4. I'm just taking a rough number, right? I'm just taking a rough number. Let's say the mean value comes out to be 20.1, right? Okay. So what will happen? Delta A1 is going to be difference of this. So delta A1 is going to be 20.1 minus 20.1. It is going to be 0. Delta A2 is going to be 0.1. Just like that. Delta A3 is going to be 0.2, right? Delta A4, 20.1 minus this, it is going to be 0.3, right? So this is going to be the absolute errors. Then you will get the mean of these absolute errors. Delta A1 plus delta A2 plus delta A3 plus delta A4 divided by 4. So the mean absolute error is going to be delta AM, right? So just add them up. 0 plus 0.1 plus 0.2 plus 0.3 divided by 4. That will give you the mean absolute error, right? So now you know the mean absolute error and the mean value, true value, right? Ratio of these two things is the fractional error or the relative error of this data set, right? So understand once again, if you have a singular data, right? If you have one observation, in that situation, what will happen? Delta A1 upon A, that will give you the relative error of that particular situation. If you have a data set, if you have multiple measurements, why have you taken multiple measurements? Because the true value was not there, right? We have measured it multiple times so that we can get the true value or the mean value, right? Once we know the true value or the mean value, we have figured out the individual absolute errors. We took the mean of those absolute errors. We called it mean absolute error, right? Okay. So now what we are going to do is the ratio of mean absolute error to the mean value or true value is the relative error of this data set. Okay. I hope the idea is very, very clear, right? This is the, like many books are giving you the different value, different definitions, and this is the main reason, right? Some books are giving you that relative error is simply delta A1 upon A, that is the absolute error upon true value. Some books are telling you that it is mean absolute error upon mean value. So both are same things, right? Don't get confused in it. I hope the idea is very, very clear. Let us now move on and talk about the next thing, which is percentage error. What is percentage error? Whenever you represent the relative error in the percentage, it's a percentage error, right? So again, if you multiply that by 100, or if you multiply the percentage error, relative error over here, so what is the relative error over here? We can say that it is going to be delta AM upon AM, right? So mean absolute error and mean value, right, into 100. So this is going to be the percentage error. But when you multiply that by 100, it is going to be percentage error. If you don't multiply that by 100, the remaining portion is this one is only relative error, right? So just here over here, you can get that delta AM upon AM into 100. That is the percentage error. All right. Okay. So this is for the data set. If you have lots of data and then you have to figure out the mean value out of it, that will act as a true value. Then you have to talk about absolute error, right? Mean absolute error, and this is how you will get it. If you have only one data, then the percentage error is going to be, right, delta A upon A into 100. That is the absolute error upon the true value into 100, right? So that's it. That's pretty much everything, right? So this is the simple concept of different types of errors, right? And after understanding the concept of different types of error, we can move ahead and talk about the next idea, which is the combination of errors, right? If we have a certain algebraic relation between the given terms, right, what kind of relation we will find in the errors of those terms? For example, let's have a look at that. These are the different algebraic relations. Some are difference, product or division, some quantity raised to the power n. We will talk about each and every case. This is a very important part of this, this section, right? In the previous years, you will find that many problems, many questions were asked from this specific section only, right? Errors in sum or difference. So how is that? Let's say we have two ropes, right? Let's say we have two ropes. Okay, this is the first one, or two rods, let's say. This is the first rod and we have added another rod to it. Okay, so what will happen? The length of first rod is L1. The length of another rod is L2. And what you have done is you measured L1, you encountered some mistake, you made some error. The error made while measuring L1 is delta L1. The error made while measuring L2 is delta L2, right? Let's say that the total length you want to get is L, right? Okay, the total summation of L1 and L2 is L. So what is there? L equals to L1 plus L2, right? My dear aspirants, if the value of capital L depends on both the length of the rods, right, both L1 and L2, and in both of them you have made a little error, can I say that both the errors will reflect in the final measurement? We will say yes, both the errors will reflect in the final measurement. So what will be the final error, right? Absolute error in the final measurement, delta capital L, right? Absolute error in the final measurement. Understand that? This L depends on, the total length depends on L1 and L2, right? You made a mistake while measuring L1, small L1 and L2 both, right? Delta L1 is a error made in measurement of L1. Delta L2 is a error made in the measurement of L2, right? In both cases you made some error, right? And what will happen? You want to get the value of capital L. You will not get the actual value of L1 plus L2. You will get some error in that as well. And that net error is delta L. So how the individual error delta L1 and delta L2 will be related to delta L, right? This is what we are talking about when we talk about the combination of errors, right? Quantities have summation L1 plus L2 equals to L. What kind of relation you will have between the errors of those quantities? We will say that in the case of summation or subtraction, the absolute errors are always added, right? So what will happen? This is a common rule, you can say, right? We can derive that as well, but that is not important in our NEET exam for now, right? So over here we can talk about this way. In the case of summation, or let's say subtraction, addition or subtraction, what will happen? The absolute errors are always added. Errors are always added, right? So I believe the idea is very, very clear, right? So right now you can say that delta L is going to be, this is going to be the net error. It is going to be delta L1 plus delta L2. I hope the idea is very, very clear, right? This is going to be the final relation in this situation. So even when we have a subtraction going on, A equals to A1 minus A2, then also the net error, the net possible error is going to be the net, absolute error is going to be the addition of individual errors, right? So delta, in the case of subtraction or summation, addition or subtraction, we will have this relation between the absolute errors, right? Okay. In the case of, what will happen in the case of product or division? So if we have this relation going on, right? If we have A equals to B into C, or if we have A equals to B upon C, in that case what will happen? Let's say while the measurement of B, the error you encountered is delta B, while measurement of C, the error you made is delta C, right? So whatever error you made while the measurement of B and C, it will reflect in the result and it will give you a final error of delta A, right? How these errors are going to be interrelated, right? Quantities have this relation. What kind of relation you will have between the errors? In the case of, you can say, product or division, we have found out that the errors are not directly added. In fact, what happens? In this case, what happens? Right, you can write down, this is the rule number 2, we can say. Okay, in the case of multiplication or division, in case of product or division, what happens? The absolute errors are not added, the fractional errors are added, right? what happens? Relative errors. Relative errors are added up. Okay. Relative errors are added. All right. That means relative error of B, that is delta B upon B. Let's write it out. Relative error of B is going to be delta B upon B. Relative error of C is going to be delta C upon C, right? So relative error of A is delta A upon A. Okay. So relative error in the result, which is this delta A upon A, is equals to relative error of individual parts, which is this, right? Summation of relative error of individual parts. So this is the relation you will have in both the cases, in this one as well as in this one. In summation, in product or division, you have the absolute errors are not related directly. Relative errors or the fractional errors are related in this way, right? So in this situation, if you want to find out what is going to be the net absolute error in the result, delta A, so what will you get? Delta A is going to be, A will go on the other side, A will go on the other side. It is going to be delta B upon B plus delta C upon C. I believe the idea is very, very clear. This is the value of absolute error of individual part, right? So now let us move on and talk about the next idea, right? Error in quantities raised to some power. So whenever you have error in quantities that has some power to it, for example, let's say that you have this relation going on. Let's say you have a quantity that is A, and that is equals to R square. For now, let us just take that, right? So A equals to R square. This is how the relation goes, right? While measurement of R, you made a little error, and you call that error is delta R. So clearly, the final result A will also have an error. Let's call that error is delta A. So what kind of relation you will have in this situation between the errors, while the quantities have this relation A equals to R square, right? So we have quantity raised to some power. What kind of error you will have when whatever quantity that has some power, you made an error while measuring it, right? Okay. So in that situation, what will happen, my dear aspirants? What will happen? You can write down R square as R into R, right? It's a product of R and R. In the measurement of this one, you made an error of delta R as well as for this one delta R, right? And you know that in the product, absolute errors are not added up. It is a relative error that is added up, right? So whatever relative error we have in the first R, which is delta R upon R, right? In the second one, again delta R upon R, right? That is added up, and that will give you the relative error in the resultant. Okay. Similarly, if we had a power 3, we have another R, we will add up delta R upon R one more time. If we have power 4, we will add up another time. If we have power n, we will add n times, right? So right now what is happening? You will have 2 times delta R upon R. Similarly, right now you can say if this is the relation A equals to R to the power n, then in that situation delta A upon A will be n times delta R upon R. Okay. So relative error in the result becomes the, whatever power is there, that will become coefficient. Whatever power we have, it will become coefficient, right? Relative error in the resultant is power times the relative error of the base, right? Now, extending on this concept, if you have this relation going on, extending upon that concept, if you have this relation going on, let's say this, let's say we have, let's say A equals to B square C cube upon D to the power 4, right? So again, we have quantities that have some power raised to them. And let's say that while measuring each one of them, you made some mistake. While taking the measurement of B, you made an error of delta B. While taking the measurement of C, you made an error of delta C. While taking the measurement of D, you made an error of delta D. All right. So what will be the net error in the final value? Let's call that error is delta A. Okay. So in that situation, what will you do? All right. In that situation, it is going to be delta A upon A. That will give you. Whatever power we have, power becomes coefficient. So here we have b to the power 2. So let's take 2 times delta b upon b plus we have c to the power 3. So it is 3 times delta c upon c. And similarly, in product as well as division, the the relative errors are always added up, right? So you see that d to the power 4 is in the denominator, so we will not subtract it. In the product as well as division, relative errors are added up, so you have to add up. Power is 4, so it is 4 times delta d upon d. I hope the idea is very, very clear. So this is the relation you are going to get in this final situation, right? So let's say you want to convert that into percentage format, right? So what will be the net percentage error in the resultant? If B has a percentage error of 2%, C has a percentage error of 3%, D has a percentage error of 5%, what is the net error? What will be the net percentage error in the value of A? If this is a question, so they are giving you the value of percentage error in each one of them. And right now it is written the relative error. So what will you do? You will just multiply that by 100. So delta A upon A into 100, that is the percentage error in the final value, right? That is 2 times delta B upon B into 100, that is percentage error of B. That is 3 times delta C upon C into 100, percentage error of C, right? And that is 4 into delta D upon D into 100, right? That is percentage error of D. So this is the relation between the percentage error, right? So you can also represent the same method and create a relation between the percentage error of the involving terms, right? So right now, if you know the percentage error in the measurement of B was 2%, so put this in place of this entire thing, put 2%. In place, let's say they are giving the percentage error of C is 3%. So in place of this entire thing, put 3%. And for D, let's say the percentage error they are giving is 5%. So in place of this whole thing, put 5% and then just add it up, right? The 2 into 2, 3 into 3, 4 into 5, and then add it up, you will have the net percentage error in the final value, right? So this is how you will get about it, right? This is how you can move about it. So let's move on and talk about the next idea, which is the dimensional analysis, right? So let's start talking about the concept of dimensional analysis. All right, to understand the concept of dimensional analysis, let us start first have a look at what are all the topics that we have to cover. My dear students, to understand the concept of dimensional analysis, we have to understand these subtopics. So without any further delay, let us start understanding the first concept, which is physical quantity. So what is a physical quantity? My dear students, you know that there are so many things around you that you can measure directly. For example, I can measure the mass of this object, right? So the thing that I am going to measure is going to be a physical quantity. What about this thing? Let's say I have this object, right? This is a very famous object of this class. So I want to measure the length of this object. Again, the length of this thing will be measured, so it will be a physical quantity, right? So right now, what is going to be a physical quantity? You can say that the quantities which can be measured by a measuring instrument, that will be called as a physical quantity. And all the physical quantity are going to have will have two terms, right? Will have two parts in it basically. For example, if I have an object that has some mass to it, let's say 500 grams is the mass of this object. So 500 and grams, right? Let us say if I have this object and I want to measure the length of this object with the help of this thing. So I said, let's say it is 15 centimeter, right? So every measurement is going to have two parts. First is a numerical part. Second will be unit. First will be a numerical part. Second will be a unit. So you see that every measurement will have a unit, that is U, right? And a numerical value, which is n. So n into u is going to be the final thing, right? So every physical quantity will have two things. First is going to have numerical part, right? And second is going to be the unit of that thing. A numerical part and unit, numerical part and unit, right? Now, how many types of physical quantity do we have right now? We have three different types of physical quantity. Again, a very basic thing: fundamental quantity, derived quantity, and supplementary quantity. Let's talk about what is fundamental quantity. Here you have it. So when we talk about the fundamental quantity, my dear students, we have these quantities available as fundamental quantities, right? When we talk about length, right? For example, what is a fundamental quantity at the first place? So anything that cannot be represented in any other terms. For example, if I want to measure the length of any object, let's say I want to measure the length of this box, right? I want to measure the length of this box, right? So I cannot get the length by measuring time, by measuring temperature, right? Any other thing, if I measure it, I will not get the exact value. I will not get any information about the length, right? If I want to know the length of this object, I have to measure that directly, right? So my dear students, that will be called as, that is why it is called as a fundamental quantity, right? So what is a fundamental quantity? A quantity which is independent of every other thing, which is independent of all other quantities, and if you want to know about those quantities, you have to measure them directly. They are called as fundamental quantities, and there are 7 such fundamental quantities, right? If you talk about length, length is a fundamental quantity. If you want to know the length of an object, you have to measure length directly. If you want to know the mass of an object, by measuring length, you will not have any idea about the mass. So you have to know the mass of the object directly. Similarly, the time, electric current, temperature, amount of substance, and luminous intensity. These are 7 fundamental quantities. If you want to know any information about these things, you have to measure them directly, right? And these are the units and symbol attached to them, right? What about the other quantities, derived quantities, right? For example, speed, for example, force. So all these quantities for which you can measure some fundamental quantities and calculate them, right? They are called as derived quantities, derived from something, right? So any physical quantity that can be derived by, the fundamental quantities is the derived quantity. For example, speed is distance over time, right? Speed is distance over time. So what is distance? A fundamental quantity. Length, time, again a fundamental quantity. So speed can be represented in terms of fundamental quantities, length and time, which is why speed is a derived quantity. What about force? The force is mass into acceleration, all right? And acceleration can be further converted into change in velocity over time, right? And change in velocity can be written as, velocity. What is velocity? We can say that. What is velocity? We can say that it is a displacement over time. So velocity can be further represented in terms of, displacement and time, right? So displacement is length and time is time, right? Again, another fundamental quantity. So we can say that right now we can break down force into mass, length and time, right? So any derived quantity can be broken down eventually into a set of fundamental quantities, right? So these are the derived quantities, right? Now let's talk about the supplementary quantities. What is a supplementary quantity, my dear students? So there are certain set of quantities we cannot derive any in terms of any fundamental quantity, right? Rather, they comes out to be unitless if we try to derive them. For example, let's say we have a plane angle. So right now you see that, let's say that we have an arc like this. Let's say we have an arc like this. Okay. We have an arc like this. Okay. And right now what is happening? We want to find out what will be the angle subtended by this arc at the center of the circle. Let's say this is point O. What will be the angle, plane angle subtended by this arc over here? Let's call this arc is AB. What will be the angle subtended by the arc at the center O, right? So over here we can say, let's say this angle is theta, plane angle is theta. So right now, plane angle is going to be arc upon radius. Let's say a radius is R, right? So arc upon radius. My dear students, you will be measuring the length of arc in, let's say, meters. So the radius will also be in meters. Meters upon meters will cancel out and the whole thing will come out to be dimensionless. In the second case, solid angle, just like the plane angle is subtended by a arc, right? Solid angle is subtended by a given area. So we have a solid body and we on the top of that solid body we have, let's say, a surface. So imagine let's say we have any spherical surface like this, and on top of that we have a small spherical surface. So how do we say that? let's say we have this small spherical surface like this. On this spherical surface, we have a small area. This little patch, if you try to join this little patch at the center, right? So the angle subtended like this will become the solid angle, right? So it is subtended by an area. Plane angle is subtended by, let's say, an arc, and the solid angle is subtended by an area, right? Let's call this area is A, okay? And the distance from the center here is R, right? So area over R square, right? The solid angle is area that is subtended the solid angle over upon the square of the distance from the center, right? So area over R square, area will have a unit of, a square meter. So R square will also be square meter. So it will cancel out. So this will also again be a unitless quantity. Now, my dear students, we can say that plane angle as well as solid angle, they do not seem to have any unit at all, which is why we have assigned them a value. This ratio arc upon radius, this ratio is assigned as a unit of radian, right? And the ratio of area upon square of distance, this is assigned as a unit of steradian. All right, so it is written over here. So it is radian and steradian. I believe the idea is very, very clear. Let us now talk about the units. So as you have seen that, right? Units, basically measurement of any physical quantity involves comparison with a certain basic value. So right now you see that I want to measure this particular thing. I can compare it against this scale. I can also compare it against this scale, right? So I can also compare against this scale like this. So measurement of any particular thing involves the comparison of one thing with other, right? So right now you see that so the unit that you are going to choose should be internationally accepted, and there are certain systems behind it, right? The most common system right now that we are using is SI system, which is international for the entire thing, right? But there are other systems as well, CGS, FPS, MKS. There are a bunch of different systems used in different parts of world. All right. So in the CGS system, centimeter gram second system, the unit of length has centimeter, unit of mass is grams, and unit of time is seconds. Similarly, in FPS system, unit of length is foot, unit of mass is pound, and unit of time is second. In MKS system, unit of length is meter, unit of mass is kilograms, unit of time is second. So this is how it goes, right? Okay. Now about this idea, dimensions, right? So what do you mean by dimension, right? Understand that dimensions are power to which the fundamental quantity must be raised so as to represent a given physical quantity. What do you mean by that? Let's understand in this way. Let's talk about fundamental quantities first. So these are the 7 fundamental quantities. They all have a certain dimension. So length has a dimension L, mass has a dimension M, and so on. Time has a dimension T, electric current has I. So in some books for current, they are also using the dimension A, right? It's if you are using I or A, it's the same thing. For temperature, it is kelvins. In some books, they are using the word theta, right? So they are not radian. Amount of substance is mole, and luminous intensity is candela. So these are the dimensions for the fundamental quantities, right? So now what do you understand by the definition? Dimensions of any physical quantities are powers to which they must be raised to represent that given quantity. So here you have it. Length is a fundamental quantity, right? But what about area? Area is not fundamental quantity, right? So area is, let's say this is L, and this is, let's say, a square. So for this one, it is going to be L square, right? What will be the dimension of this thing? Nothing about it. Area is L square, right? This is a fundamental quantity. This fundamental quantity must be raised with this power so as to represent this. So the dimension of this thing is going to be 2, right? Okay, for the length, right? What about volume? For the volume, it is L cube. So the power of fundamental quantity we have to raise this, we have to raise this fundamental quantity with the power 3 so as to represent the volume. So for this situation, the dimension is going to be 3 for the length, right? So I believe the idea is very, very clear. So for example, if I talk about, let's say, force, right? So force cannot have a direct, unit. right? It does not have its own unit like that. Newton is SI unit, we know that, but in terms of fundamental and derived unit, if we have to find out, force is mass into acceleration, right? So right now if you see, force can be represented like this: mass is m, right? And area can be the unit of area can be not a sorry acceleration. The unit of acceleration should be uh, change in velocity over time, right? And you know that velocity is displacement over time. Displacement is L, time is t. So velocity is displacement over time. So it is LT minus 1. All right. And this t is t only, right? So for acceleration, the dimensional formula for acceleration will be LT minus 2. All right. Dimensional formula for acceleration will be LT minus 2. So put the value LT minus 2 over here. So it will be MLT minus 2. All right. So similarly, right now you can say that the force, which is a derived quantity, depends on these powers of fundamental quantity. It depends on mass to the power 1, length to the power 1, while time to the power negative 2, right? So this is how you can understand that every derived quantity can be represented to the sum powers of fundamental quantity, and that is what you mean by dimensions, right? So read that again. What is dimension? Dimensions of any physical quantity are powers to which the fundamental units are raised in order to express the derived unit of a quantity, right? So right now you see that the force is a derived unit, right? And if you want to represent that, we have used fundamental quantities, and the powers to which they must be raised to represent that are the dimensions of force, right? Similarly, we can talk about the other thing, right? There is very interesting application, or you can say there is very interesting concept which is attached to the dimensional analysis, which is called as principle of homogeneity. Now, in most cases, it's an extension of your common sense, right? How is it a common sense? Understand that. How is it a common sense? You see, let's say if I have this body, right? I want to add the mass of this body with the mass of this body, right? I can do that because mass can be added to the mass, right? But what if I have the mass of this body, let's say 500 grams, and I have the length of this body, let's say 5 meters, right? So 500 grams and 5 meters cannot be added, right? Okay, 500 grams and 5 meters cannot be added. Grams and 5 meters cannot be added. Why so? Because one thing is representing mass and the other thing is representing length, right? So if you are adding two things, they must share the same dimension, and this is the principle of dimensional homogeneity, right? Principle of homogeneity, that anything that is added or subtracted, anything that is equated, right? If there are two things, if you are using, let's say, A plus B equals to C, right? This equals to sign is coming up. That means whatever dimension we have on the right side, the same dimension we have on the left side, right? And over here, you just focus, since two things are added, whatever dimension is shared by the first value, the second value which is added should also have the same dimension, because only two things with the same dimension can be added, and this addition is not possible, this subtraction is not possible. Similarly, two things cannot be compared if they do not share the same dimension. I cannot say that 500 grams is more than 5 meters, right? That doesn't make sense, right? One thing has different dimension and the other thing has different dimension. You cannot compare it. So my dear students, we can say that if two things A and B are there, they have either plus sign, minus sign, equals to sign, greater than sign, or less than sign. In all such situations, if there are two quantities A and B, then in all these situations, they should share the same dimension. They should share the same dimension. Got it? Okay. So if there are two things A and B, and they have this sign in between them, so they must have the same dimension. Let's move on and talk about the next idea. So here we have it. A wave is represented by y is equals to a sine at minus bx plus c, where a, b and c are constants and t is seconds and x is in meter. The dimensions of a, b and c are. What will be the dimension of a, b and c? So we have this thing going on for us. Y is equals to a sine at minus bx plus c. A sine at minus bx plus c. At minus bx plus c. Right? So a, b and c are constants and t is in seconds and x is in meter. The dimension of a, b and c we have to find out. How can you do that, my dear students? Let's understand that. What will be the dimension of a, b and c? Understand, anything that comes after sine, that must be an angle. So this whole thing is representing an angle. Right? And you know that angle is arc upon radius, right? Meters upon meters. That has no dimension, right? Okay. So right now, the angle, this whole thing that is representing an angle is a dimensionless number, right? So the dimension of this whole thing is, at minus bx plus c. The dimension of this whole thing is m0, L0 and T0. This thing does not have any dimension at all, so it's a dimensionless thing we can say. So the dimension of this whole thing should be a dimension of angle, which is m0, L0, T0, right? So AT, T is, what is the dimension of, now think about it, right? If there is basically equals to sign, plus sign, negative sign, I have told you that then those things must share the same dimension. Here I have told you, if two things are separated by these signs, they must share the same dimension. So you see that all of these things are dimensionless, right? So this and this and this, you see that all of them have a plus, minus, equals to sign in between them, so they all must be same in dimension. So AT is dimensionless, BX is dimensionless, and C is dimensionless as well. So what is the dimension of C? Dimension of C is same as this, M0, L0, T0, right? Okay, M0, L0, T0, right? What is dimension of BX? We can say dimension of BX is also same, M0, L0, T0. So x is what? Displacement. It is in meter, right? So dimension of x is going to be L. It is M0, L0, T0. So L will go on the other side. You can write down, because the answer does not have M0, L0 in the first one. So we can, without any problem, we can put it M0, L minus 1, T0. Or this thing can also be written as L minus 1, which is not a better way of writing it, but it's still, because the options are there. Now the last one is AT. So AT also has a dimension M0, L0, T0. Right. AT also has the same dimension. AT also has the same dimension M0, L0, T0. Right. So dimension of A is going to be M0, L0, T minus 1. So this is nothing but T minus 1. Dimension of A is also going to be T minus 1, right? So we can say that for dimension of A, it is T minus 1. Dimension of B, it is L minus 1. And dimension of C is going to be M0, L0, T0, right? So which is the correct option? Which is the correct option? T minus 1, L minus 1 and M0, L0, T0. So it is the option B, right? So let's have a look at that. This is the correct option in this situation, right? This is the correct option in this situation. I believe the idea is very, very clear. Let's look at this question as well. The velocity of a particle is given as this, right? So velocity is given as, what is this t in the bracket? It is giving you the velocity at time t is at square plus bt, at square plus bt plus c upon t square plus d. Right? Velocity of a particle is given with this expression. This is saying that velocity at time t, it is not v into t, right? So velocity at time t is this, right? Where a, b, c and d are constant. The dimension of AB upon CD is going to be, what will be the dimension of AB upon CD? What will be the dimension of AB upon CD? So now again the principle of homogeneity will help us. Principle of homogeneity will help us. Think about it. We can say if we have equals to sign between this and this, so this and this whole thing, they all have the same dimension, right? So dimension of AT square, this entire expression, and dimension of this thing is same, right? So AT square, we don't know the dimension of A, T is time, so we have dimension of A, T square is this, and velocity, for velocity we have LT minus 1, we know that, right? So dimension of A is going to be, T square will go on that side, it is LT minus 3, alright. So I believe that T square will go in the denominator, it will become LT minus 3. So dimension of A is going to be LT minus 3, okay. What will the dimension of B? So this part, this portion also have the same dimension as dimension of velocity, because equals to plus sign, anything that is separated with these signs have the same dimension. So we can say dimension of V and dimension of BT is going to be same, right? So dimension of B and dimension of T, which is time, it is LT minus 1. So T will go on the denominator, right? And then when it is going to come up, it is going to be LT minus 2, right? So dimension of B is going to be LT minus 2. I believe there is no problem in that part. Now let us talk about the next part, which is dimension of this thing with the dimension of velocity. So dimension of velocity will be same as dimension of this thing, dimension of C upon T square plus D. Now, if you focus, my dear aspirants, so here you have T square plus D. Two things are added up in the denominator. If two things are added up, they must share the same dimension. So dimension of this expression and this expression must be same, right? If two things are added up, they must share the same dimension, right? If two things are added up, they must share the same dimension. So right now what we will say, the dimension of T square and dimension of D must be same. So over here you can write separately, dimension of T square is same as dimension of D. So we can say T square has dimension of this is the dimension of D, right? Without any problem you can say that, right? So the denominator, right, let's say if you are adding length and length, the dimension will be, the final value will be length, right? If you are adding meters to meters, the final value has dimension of length. If you are adding kilograms to kilograms, the final value has a dimension of mass. So if you are adding T square and D, so they have the same dimension, so same dimension added up, so the denominator has a dimension of T square, right? So the numerator has a dimension of C, let us say. So T square plus D, the dimension of the base is going to be T square. And for the velocity, dimensional formula is going to be LT minus 1. For the velocity, the dimensional formula will be LT minus 1, right? So the dimensional formula for C is going to be LT minus 1 will be there and 2 will be added up. So it is LT plus 1. Alright. So this is it. So you know the dimensional formula for A, B, C and D, right? All the values are given. You can figure out the dimensional formula of AB upon CD by yourself, right? So just put the values. A, LT minus 3, right? Dimensional formula for B is LT minus 2, right? Dimensional formula for C is LT plus 1. And dimensional formula for D is T square, right? This is the dimensional formula of AB upon CD, alright? So that's it. Just put the value of similar things in one place. So L and L will come together, T and T will come together, right? And that will give you the answer. Now I'm leaving that to you, right? Just do that and find the correct option, right? So that's it. Let's move on and talk about the next one. Which of the following combinations of three-dimensionally different physical quantities x, y, z? So they are giving you x, y, z are three-dimensionally different. If one is length, one is volume, one is, let's say, area, anything, right? They can never be meaningful quantity. Which of this will never represent a meaningful quantity, right? So you know that two-dimensionally different quantities cannot be separated by that sign, plus, minus, equals to, greater than, less than. If two things are dimensionally different, they cannot have this relation between them, right? So you see that x square minus y square, right? All of the quantities have a product, So product is possible between different dimensions. That is a separate thing. But what about this thing? Plus minus equals to greater than less than. What about this x square and y square? Right? If x and y have a different dimension, then a square of x and a square of y will surely have different dimension altogether. Right? So they cannot have same dimension. They cannot be subtracted. So this expression is never possible. So option C must be true. Right? Application of dimensional analysis. Now, after understanding the concept of dimensions, we can now talk about where are we going to apply it. We know how to write the dimensional formula of different physical quantities, and now we want to apply the concept of dimensional analysis. So the first application is going to be to convert the units. How to do that and why we need to do that? Now understand. My dear aspirants, many times when we want to convert the units, we know the conversion factor. For example, if I know the length of this pen is 10 centimeter, right? And if you have to convert in millimeters, you know the conversion factor is 10. You will multiply this value by 10 and you will say that the length of this pen can be written as 100 millimeters, right? Similarly, if you can convert into other units by you multiplying or dividing by the conversion factor, right? Similarly, if you know the mass of this object, let's say it is 200 grams, right? Grams, and you want to write down in kilograms. So there is a conversion factor for it, which is let's say kilogram. For the kilogram it is 1000, and you want to convert it in kilogram, you will divide it and you'll say it is 0.200 kilograms, right? So you were able to do that because you had an idea about the conversion factor. But my dear aspirants, there are various derived quantities. For example, Newton per meter square, and you want to convert into dyne per centimeter square, right? By what value you are going to multiply right now? Right? By what value you are going to divide right now? There are so many different quantities where you don't know the conversion factors, right? And in all those cases, you need to know the dimensional analysis so that you can convert the units, right? So you know that, like this situation, there is a Young's modulus of a body. So Young's modulus is defined for materials, right? So what is happening? We have this material with us. We have defined the Young's modulus for this material, right? If we change the material, there is a constant attached with every material. We are calling it a Young's modulus, right? So Young's modulus for this metal is going to be a separate value, right? So for the steel, it is this, right? 19 to the power 10 Newton per meter square, right? This is the value for the Young's modulus of a given material, steel, right? What we want to do is we want to express it in the dyne per centimeter square, where dyne is the CGS, centimeter gram second unit of the force. So we don't know the conversion factor, and in this situation we have to use the dimensional analysis method. So what is that and how to use it? Understand that when we are converting the units, there is one common concept, right? What is the concept in this? What is the concept in this? So 10 centimeter, 100 centimeter. Can I say that 10 centimeter or 100 millimeters, they are representing the exact same value? If I am calling the length of this pen is 10 centimeter, or I am calling the length of this pen is 100 millimeter, I am saying the same thing. They are representing the same value, right? Here the unit is different, the numerical value is different. Let's call that numerical value is N1. Here this numerical value is different. Let's call the numerical value here is N2, right? Here the unit is different. Let's call the unit here is U1, and here the unit is different. Let's call the unit here is U2, right? N1 and N2, the numerical value in one system and numerical value in second system are different. Similarly, the units in one system and second system are different, right? But if I talk about N1 U1 and if I talk about N2 U2, right? Okay. If I talk about this thing, they are going to be the same. Yes or no? This thing 10 centimeter and 100 centimeter, they are representing the same thing. This N1 U1 whole thing and N2 U2 this whole thing, they are representing the same thing. I believe the idea is very clear. Even when the unit is converted, right? Even when the unit is converted, they represent the same things, right? So now N1 is the numerical value, U1 is the you know, U1 is the unit in the first case. So let's say that in the first system, the unit of mass is, let's call it M1, L1 and T1, right? And let's say that they are powers A, B and C, right? So basically what will happen, the dimensional formula of this thing is not going to change. In the first thing it is length, in the second thing it is length. So in both, while converting it, the dimensional formula is going to be the same. That means the powers that you are raising to M, L and T, the fundamental quantities, they are going to be the same, right? So here it is N2. And again, since you are only changing the unit, it is still the same value, same quantity, same physical quantity. So basically, the dimensions A, B and C are going to be same. Just the base will change, M2, L2 and T2, right? Let's call it powers are going to be the same, right? So basically, if you want to know the value of N2, it is going to be N1, M1 upon M2 to the power A, L1 upon L2 to the power B and T1 upon T2 to the power C, right? Now let us try and understand with the help of an example, this example that we have here. So you have the Young's modulus which is given in Newton per meter square and you want to convert into dyne per centimeter square. In both situations, you are representing the Young's modulus only, so we are dealing with the same dimension. So right now, with the principle of dimensional analysis, we can say that since we are dealing with the same quantity, so N1 U1 in one system of unit is same as N2 U2, right? In the first case, the value is N1, 19 into 10 raised to the power 10. What is the unit over here? Newton per meter square. If you want to write out the dimensional formula against it, in the first step, let me write it Newton per meter square. In the second case, N2 we don't know and U2 is going to be dyne per centimeter square, right? Okay. Now, we can say that even if we are changing the system of unit, we are still representing the same quantity, which is Young's modulus. So the dimensional formula over here and the dimensional formula of over here will be same, right? So just put it 19 into 10 to the power 10, all right? For Newton, it is MLT minus 2. So, or let me calculate the Newton per meter square dimensional formula separately over here. For Newton, it is MLT minus 2. And for meter, it is L2. So, it is going to be ML minus 1 T minus 2, right? Got it? So, for Newton per meter square, I can use the dimensional formula ML minus 1 T minus 2. All right. So, on one side, we have ML minus 1 T minus 2. All right. Let's call it M1, L1, T1. And on the other side, we have N2, right? This thing will also have the same dimension because they are representing the Young's modulus. So, but let's say the bases are different. It is going to be M2, L2 and T2, right? L minus 1, T minus 2. All right. I believe the ideas are very, very clear, right? So, what will the value of N2 over here? So, N2 is going to be 19 into 10 to the power 10. Okay. So, it is M1 upon M2. Right. Here we will have L1 upon L2 to the power minus 1. Here we have T1 upon T2 to the power minus 2. Right. Okay. Now in the first system, M1 is representing the mass. So right now in the first system we have MK system going on for us. And here we have the CJ system going on for us. Right. So M1 in the first system, mass is measured in kilograms. M2 is the second system where the mass is measured in centimeter grams, right? So in the first system, M1 is kilogram. So in the same step, I'm changing it. It is 10 raised to the power 10. In the first system, it is kilograms and M2 is grams, right? L1 upon L2. In the first system, length is measured in meters because it is MKS, right? Meters. And second system, length is measured in centimeters. And time is measured in both the cases in seconds. So it is seconds upon seconds, right? So you see that kilogram upon gram, so it is 1000, kilogram has 1000 grams, 1000 grams upon grams, you can cancel out the grams, so it is 1000, right? So kilograms upon gram, you can write down 1000. Meters upon centimeter, so meter can be written as 100 centimeter and then centimeters can be removed, so we have 100. And seconds to second, it is 1, right? So you see that 10 to the power 5 can be multiplied, so N2 will be 9 to the power 15. So I believe the idea is very, very clear, right? And that should give you the crystal clear idea about how to convert the unit from one system to the other system, right? Okay, so this is the next application of dimensional analysis, which is the to establish a relation between different physical quantities, right? It helps us. Now, this is very, very important, and there are so many questions that are asked on this particular application, and we can understand that with the help of an example as well. Now, with the help of dimensional analysis, we can find out the relation between the given physical quantities. How? Let's have a look at that. Let's say area, velocity and density, they are the base units, right? They are the base units. Then the dimensional formula of force can be represented. So we want to represent force in terms of these base units, area, velocity, density. No problem, right? We can find the relation between any two physical quantity with the help of simple dimensional analysis. How to do that? To do that, let's take the step number 1. What is the first step? Right, this is one of the previous year NEET examples, right? So first of all, you want to find out what will be the dimensional formula for force. So let's say the dimensional formula for force is A to the power. We want to represent it in terms of area, velocity and density. So let's say that it is area to the power A, velocity to the power B and density to the power C, right? You don't want the dimensional formula of force in basic units, which is mass, length, time. We don't want that. We want the dimensional formula for force in these base quantities. We want to consider them as base quantities or fundamental quantities and then find the value of dimensional formula for force, right? No problem, right? So this is the first step, right? In step 2, you have to solve it out and get the value of ABC, right? So just solve it out and somehow get the value of ABC. Once you have the value of ABC, put it back here. So you have the dimensional formula of force, right, in terms of area, velocity and density. So we have to find the values of ABC now, right? Now, you know that by default, the dimensional formula for force is mLT minus 2. Mass into acceleration, so it is mLT minus 2, right? Area is L2, and the power is A. This is velocity, it is LT minus 1, the power is B. This is density, right? This is density, so it is L cube, ml cube. Density is, right? Density is mass per unit volume, so it is m upon L cube, so it is ml minus 3, right? So density is ml minus 3 to the power C. Right, so I believe the ideas are very, very clear, right? So just solve it, mLT minus 2, right? We have m to the power C over here, we have L to the power 2A and L to the power B and L to the power minus 3C over here, right? And then T, we have only minus B, right? So now, by the principle of homogeneity, whatever we have on the left side is separated by the equals to sign. So these things must have the same dimension. That means the powers must be same, right? So power of m on the left side is 1. So this is going to be step number 3. So here the power is 1, here the power is C. So C is equals to 1, right? Here the power of L is 1 and here the power of L is this 2A plus B minus 2C, 2A plus B minus 3C. That is equals to 1 over here, and here the power of time equals to minus 2, so minus 2 equals to power of time, which is minus B, so B is equals to 2. C is 1, B is 2, just put the value over here, 2A plus 2 minus 3 equals to 1, so it is minus 1, it will go on the other side, so A will become 1, right? So now you know the value of A is 1, B is 2, C is 1, right? Just put the values over here. A is 1, B is 2, and C is 1, right? So A V square D, A V square D is the option B, so option B is going to be your correct option, and this is what you need to choose, right? A V square into D. So this is again based on the simple principles of homogeneity and simple application of dimensional analysis, right? Now let us talk about this thing, limitations of dimensional analysis. My dear aspirants, you know that we can find the relation between a given physical quantity, right? But with the help of dimensional analysis, there are certain things you cannot do, right? For example, if in the relation there is some constant, right? Then that constant we cannot figure out with the help of dimensional analysis. For example, if you want to find out the relation between the time period of a pendulum, let's say there is a pendulum, right? It is hanging with this thing, right? It has a certain length. This bob has a mass m, right? And it is moving to and fro like this. So it has a time period t. We can figure out the value of its time period. We can figure out the relation of its time period with the available parameters, right? And let's say the value of acceleration due to gravity over here is g, right? With the same method, if you try to find out the relation, we will say that the time period will come out to be proportional to under root L upon G, right? But time period is 2 pi under root L upon G, right? 2 pi under root L upon G, right? Here, there is no way in the dimensional analysis you could calculate this value of 2 pi. You cannot get the value of this constant by any dimensional method, right? So dimensional analysis can give you the relation between the quantities, but that relation does not have to be mathematically accurate. It is dimensionally correct. The relation will always be dimensionally correct, but it need not to be mathematically correct as well. Why? Because the constants involved cannot be calculated with the help of dimensional analysis, right? Okay. So dimensions does not depend on the magnitude, all right. Due to this reason, the equation x equals to ut plus at square, you know that the exact correct equation is x equals to ut plus half at square. That half is not there, but still when you find out the dimensional accuracy, the dimensional formula of ut, dimensional formula of this and dimensional formula of this, they all comes out to be same, right? So even if it is dimensionally correct, but still it is not the exact correct equation, right? It is dimensionally correct, thus a dimensionally correct equation need not to be physically correct. Understand one more way, right? Here you have x equals to ut plus at square, right? So this is displacement, the dimensional formula for that is L. This is velocity, Lt minus 1, and then this is time. So Lt minus 1 and t, again only L. So this term also has a same dimension L, which is the dimension of x, and they are separated by equals to sign. So till now we have the same dimension, we are going well, right? Dimensional formula for acceleration is Lt minus 2 and for time is t2. So for this one again we have L. So you see that all the expressions have the same dimension over here. If this one and this one, and they are separated by a plus or an equals to sign, and they should have the same dimension. So the equation is dimensionally correct, dimensionally homogeneous, right? But the dimensionally correct equation is not actually physically correct. Why? Because the equation is ut plus half at square. That half is not there, right? So the constants are not included in the dimensional analysis. So constant of proportionality of any equation cannot be deduced by the dimensional analysis, right? And over here, the method is applicable only if relation of product or ratio type, if phase in the cases of addition, subtraction, power, exponential, trigonometric relation. These kind of relations you cannot derive or deduce from the dimensional analysis, right? So this is the simple application and simple limitation of dimensional analysis. And I believe till here everything must be crystal clear, right? So this was everything about the dimensional analysis, my dear aspirants. Now we can move on and talk about the next idea, which is the concept of vernier caliper and screw gauge. So without any further delay, let us start talking about it and complete that as well. Now let us understand the concept of vernier caliper and screw gauge. And to understand the concept of vernier caliper and screw gauge, you need to know about a few things, right? mainly least count and then the process that you need to take the reading out of these two instruments. My dear aspirants, you know that you can take the measurement of length with the help of a simple scale as well, but it has certain limitations when you consider the resolution of this thing. When you talk about a vernier caliper, you can talk about more precise measurement of any particular length, right? So we will talk about that now. Right, so let's have a look at that. So this is the vernier caliper, right? This is the vernier caliper in front of you, right? So you see that there are jaws in it, right? So there are jaws in it. So these are the jaws, and they are used for measuring the inner things. For example, if you want to know the outer diameter of this thing, for example, this is I should be saying, if you want to know the outer diameter of this pen, right, I can use these jaws, right? Okay, but what about this one? If I have a pen cap over here, let's say, or let's say if I have this little small ring over here, right, and I want to know what is the inner diameter of this ring, so I'll be using these jaws. I'll be using these jaws like that, right? So what I'll do, I'll just put this thing over here, right, and then I'll stretch it out, right? So just like that, with the help of these jaws, I can measure the inner diameter of this ring. So these things will tell us the outer diameter, and these jaws will tell us the inner diameter, right? There is one thing as well. So considering if this expands to a certain value, right? You see that, look at this little stick that is coming out of it. The degree to which you open this vernier caliper, this stick pops out of the vernier caliper by the same amount, right? So whatever reading you take for this measurement, same reading is applied to the unit of this particular part, right? So there are cases in which you want to measure the length of or you say the depth of any particular thing, right, and you cannot actually measure it. So in that case, measuring the depth can be done with the help of this vernier caliper as well, right? Because whatever, as I said, whatever value is there between these two things, the same value you will find as an extension of this particular part, right? So these are the different parts of this thing, right? So this is the stem that is used for measuring the depths. Now as you can see that, unlike a normal traditional scale that has only one scale and all the values are pointed, or you can say printed on it, you have two scales in the vernier caliper as well as on the screw gauge, right? One scale is the main scale that is extending all the way till the end, right? And the other scale that slides above it also has some markings above them, above that as well, right? It also has some markings above it, right? So this scale that slides over it is called a sliding scale or vernier scale, right? So there are two scales in it. One is the main scale and the other one is the sliding scale, right? And the markings are available on main scale as well as on the vernier scale, right? Okay, the gap between the marking is not same, however, right? The gap you have the markings on between these main scale readings and the gap between the markings of vernier scale reading need not to be the same, right? I believe the idea is very, very clear. My dear aspirants, if you want to talk about what is the least count, what is the smallest value you can measure out of a given vernier caliper, that thing depends on the gappings, right? The gap that you have available between the markings, right? So you see that whatever gap is available between the markings of the main scale and whatever gap is available between the markings of the vernier scale, that decides the least count of a given vernier caliper, right? For example, let us say that while taking a measurement, if n vernier scale divisions coincide with the n minus 1 main scale divisions, right? If that is happening, then what will happen? N minus 1 main scale divisions are same as n vernier scale divisions, right? Let's say that this is the main scale, right? And you take this little section of the main scale and you have some markings on it, right? Okay. In the same gap, you have different number of markings on the vernier scale, right? And you found out that the number of markings on the main scale is same as the number of markings on the vernier scale minus 1, right? In this particular situation, n minus 1 main scale division are same as n main scale division. Then in that case, what will you get? one vernier scale division is same as n minus 1 upon n main scale division, right? Okay. In this specific situation, when this is holding true, right? And in that case, the least count is the difference of gaps, right? The difference between one main scale division and one vernier scale division will give you the least count, which is in this case is main scale division upon n if you solve it, right? But my dear aspirants, this is not always going to be the case. Let's have a look at this question and then understand how to take the final measurement out of it. So here we have it. 1 centimeter on the main scale of Vernier caliper is divided into 10 equal parts, right? We have main scale and we have vernier scale, right? We will understand this thing with the help of this question. So question is saying that 1 centimeter on the main scale of Vernier caliper is divided into 10 equal parts. Good. If 10 divisions of vernier scale coincide with 8 small divisions of the main scale, 10 divisions of vernier scale coincide with the 8 divisions of the vernier scale. Okay. The least count of the caliper is. Try and understand it. What do you mean by that? Think about it. If I'm building a home, right, and I want to go from one floor to other floor, right, I have to make steps, right? And you may have seen that in some homes, they make larger steps, taller steps, right? And in some homes, they make tiny steps, right? Okay. So let's say the total height that they'll take you is same, right? Whatever height these steps are going to take you from base to the bottom, base to the top, is same as whatever height they will carry you from base to the top, right? The total height they will take you from base to the top is same in both the cases, right? But the number of step is different, right? Same thing is happening in the case of vernier caliper, right? In the vernier caliper, there are two scales, as I said, right? And the gaps are different. The main scale has different number of gaps and the vernier scale has different number of gaps. And in this situation, what is happening? In the same distance, to cover the same distance, to cover the same gap, right? Take this gap on main scale and take the same gap of vernier scale. We found out 1 centimeter of the main scale of vernier caliper is divided into 10 equal parts. And what is happening? 10 divisions of the vernier scale coincide with 8 divisions of the main scale, right? 10 divisions of vernier scale coincide with 8 divisions of vernier scale. 10 divisions of vernier scale are same as 8 divisions of main scale. So this is what we have. 10 main scale, 10 vernier scale divisions, right? 10 vernier scale divisions are same as 8 main scale divisions. That is written. So one vernier scale division will be 8 by 10 main scale divisions, right? I believe the idea is very, very clear, right? The least count of this caliper is going to be, so very easy. So least count is the difference between the main scale division and vernier scale division, right? The difference between the gaps, the difference of step size, right? What is one main scale division over here? We have written over here that 1 centimeter on the main scale is divided into 10 equal part. So one main scale division will be, one main scale division is 1 centimeter is divided into 10 parts. So this is the smallest division on the main scale, 1 upon 10 centimeter, right? So here you can write down least count is going to be 1 main scale division minus 8 by 10 main scale division, right? One vernier scale division is this, so just put the value, right? So here you have subtracted 2 by 10 main scale division, right? And one main scale division is 1 by 10, so just put it, it is 2 by 100 main scale division, right? Which is centimeter, the unit is centimeter, so just you replace it by centimeter, 2 by 100 centimeter, right? So it is 0.02 centimeter, 0.02 centimeter, which is option B. So option B is going to be correct option in this situation, right? So I believe the idea is very, very clear. Let's talk about the next idea, which is a screw gauge, right? So in a screw gauge, again, you are going to have two, scales. One is going to be a linear scale, which is the main scale. The other one is circular scale. It is called as, the circular scale. It is a secondary scale. Again, just like the vernier caliper had two scales and the final reading was a combination of those two. Here also in the screw gauge, you have two scales, right? The main and the circular one. And the final reading will be a combination of these two, right? So How to get the meaning out of this scale? So right now you see that every time you rotate this scale, no, every time you rotate the circular scale, it moves ahead by a certain value, right? In one full rotation, whatever displacement it covers forward is called as pitch of the screw gauge, right? You rotate it one time. For example, if you just look at the screw, right, you move the nut for one entire rotation, it moves ahead for a certain distance, right? In one entire distance, whatever distance it covers, that is the pitch of that particular screw and nut assembly, right? The same thing is happening over here. The pitch of this screw gauge is in one entire rotation, what distance it covers forward, right? That is the pitch of this thing, right? So let's say that you move it ahead by n rotations and it moves by a certain value on the main scale. So what will be the pitch? Whatever distance is covered on the main scale upon the number of rotations. So what will be the pitch of this thing? Main scale reading upon the number of rotation. Okay. Okay. So least count is going to be pitch upon total number of divisions on the circular scale. Pitch, what is going to be the least count? Pitch upon total number of divisions on the circular scale, and total reading will be main scale reading plus circular scale reading into least count. Let's have a look at one numerical as well and try to solve it for the circular for the screw gauge as well. So the question is saying a screw gauge has a least count of 0.02. A screw gauge has a least count of 0.02 centimeter. Sorry, 0.02 mm. All right. And there are 100 divisions on the circular scale. So the number of divisions on the circular scale is 100. Okay. The ratio of pitch of the screw gauge to the least count of the screw gauge is. So what is pitch? Pitch is, or you can say what is least count? We can say the least count of a screw gauge is its pitch upon number of divisions on the circular scale. Divisions on the circular scale. On the circular scale. CS is circular scale, right? So least count is going to be, it is given in the question, it is 0.02 mm. It is pitch upon number of division is given as 100, right? Number of division is given as 100, okay? All right. So what is going to be the value of pitch? Pitch is going to be 2 mm, all right? Pitch is going to be 2 mm. In one full rotation, it will move ahead by 2 mm, right? Okay. You have to find the ratio of two things. Pitch of the screw gauge to the least count. So ratio is pitch of the screw gauge upon the least count. All right. So this ratio can be easily figured out, right? 2 upon 0.2, 0.02. So you have 100. This ratio will come out to be 100. I believe the idea is very, very clear, right? This is the option A, which is the correct option. Now let us move on and talk about the next idea, which is the concept of significant figures, right? So now let us start talking about the concept of significant figures. My dear students, in physics, many times this particular concept plays a very, very important role, right? Where we have to, let's say, round off a certain number, right, to a certain value, right? We have to find out what is the number of significant figure in a given value, right? How to do all those things we are going to learn in the upcoming pages with few examples. Let's have a look at that first, right? So here we have a few things, right? If you want to find out the number of significant digits in a given value, right, there are certain rules, my dear students, you have to find out, right? So first of all, we have the significance of non-zeros. So if you have a number like this, where all the digits are non-zero, how can you find out the number of significant digits out of all the available digits? My dear students, the rule is simple for all the non-zero numbers. Every number that is available in front of you, right, and is more than 0, that is non-zero, will be considered as a significant digit, right? So all of the number here, so 1, 3, 5, 5, 2, none of these is 0, right? So all of them are non-zero, right? So basically all 5 digits are going to be significant over here. The rule is very simple for the non-zero numbers, right? So here the number of significant digit is, here how many significant digits are there, or how many significant figures are there? So here the number of significant figures, number of significant figure in this value is 5 because all of them are non-zero. But the question arises when the given value has zeros in it, right? And in that specific case, you have to observe when a given zero will be considered as significant and under which circumstances we have to drop that zero, right? And it will not be a significant number, right? So to do that, we have these two examples in front of us. Look at that. We have zeros in different situations, right? And for all the specific kinds of zeros, we have certain rules, right? So the zero that comes at the trailing end, these zeros, right? And in this situation, this zero, right? These zeros that come at the end are called as trailing zeros, right? These zeros that come at the end are called as trailing zeros. What do you call them? You call them trailing zeros. Trailing zeros. These zeros that come at the end are called as trailing zeros, right? Now, after that, there is one more kind of zeros that you have over here. You see that these zeros that are trapped between two non-zero numbers, this zero, right? What about these zeros? They are also trapped between two non-zero numbers, 5 and 2. So this one as well. These zeros that are trapped between two non-zero numbers are aptly called as, you can say that these are called as trapped zeros. Trapped zeros, right? So there are circumstances where you have to find out if this zero is trapped zero or not, right? So here if you look at in the second example, right, this zero is trapped between two non-zero numbers. So right now here this zero is also going to be, this one is going to be a trapped zero, right? Trapped zero. Got it? While this zero is going to be a trailing zero. Got it? So all these things happen within your mind, right? Very quick. But just to show you as an example that there are different types of zeros in this situation, and a certain type of zero will be significant, a certain type of zero will not be significant. This is what we need to understand, right? But now if you focus on these zeros, right, you don't have any non-zero number ahead of them, right? So these zeros that come at the beginning of this thing, where you do not find a non-zero number in the beginning, all these zeros are basically leading zeros, right? Leading zeros. I believe there is no confusion about this zero being significant or not, because before the decimal place you can have any number of zeros and anyone can say with the common sense that all the zeros that are coming with it before the decimal place, anyways they are not going to be significant. So the confusion is not for these zeros. We will say that the confusion is mostly for these two, right? The confusion is mostly for these two. Right, so you can say that these are our leading zeros, right? So let us start talking about the rules now, under which circumstances a certain type of zero will be significant, right? So see that the trailing zeros, the zero that come at the end, are only significant when, right, when they come after, right? The trailing zeros can have two separate cases, right? We have the trailing zeros with a number that has decimal, right? So we have the trailing zeros with a decimal place, with the decimal place, right? And then the second possible situation is we have trailing zeros without a decimal. For example, we can have 500, 5000, right? So in this situation, we don't have a decimal place coming in front of us, right? So we can have without decimal. Without decimal. My dear students, focus on this part. We will say that whenever we have trailing zeros and the number has a decimal point in it, then all the trailing zeros will be considered as significant. So right now, these zeros will be considered as significant. So if I have like this 5.0, so this 0 will be considered as significant, and the 5 is a non-zero number, that is also significant. So in this value, we have two significant numbers, right? So we can say that If it is written like 5.00, we have trailing zeros like this, but these trailing zeros come after the decimal point, so there will be 3 significant figures in it. If I have, let's say, 4.9500, so you see that these zeros are the trailing zeros, but the number has a decimal place, so these zeros will be a significant figure. So 1, 2, 3, 4, 5. This number is going to have 4 significant figures. I believe the idea is very, very clear. If there are trailing zeros and there is a decimal place, then those trailing zeros will be considered as significant figures, right? Now, if we talk about without decimal place, let's say we have 50, we have 500, right? In the same values, if we remove 49500, right? So we have exact same things, but there is no decimal place. So right now the trailing zeros will not be significant because the number does not carry a decimal point. So in this one we have only this value as significant. So one significant figure is there in this one. Here also we have one significant figure. And here again these zeros will not be significant, only for the first 3 digits will be significant. So only 3 significant figures are there in this value, right? Now, if you talk about the reason why is so you may think in this way. Here, when we have decimal places, this tells us a lot, right? It may also tell us that the information about the instrument from which the measurement has been taken. Think about it. We can measure anything. For example, let's say we have this pen. We can measure the length of this pen with the help of this scale, right? We can measure it with the help of this scale. So we cannot measure it beyond a certain point, but we can take another vernier caliper, right? And we can have more precision. We can have another point and another decimal point after that, right? So basically the idea is very, very clear, right? It is possible that the instrument you are measuring from, let's say you might be measuring from this simple scale, right? Simple scale, right? The instrument that you are measuring from cannot measure up to 2 decimal places, right? So it can only measure up to 1 decimal place, that is why 5.0. But then you move to a more precise instrument that can give you a more detailed view up to 2 decimal places, which is why you have these 2 zeros after decimal, right? So in this situation, I always remember that whenever you have the trailing zeros and there is a decimal point, then those trailing zeros will be considered as significant, right? Okay. Now, you have the trapped zero, right? Trapped zeros are always going to be significant. So they are always going to be significant. Always going to be significant, right? So right now, if I have like this 205, so this 0 is a trapped 0, right? We have 3 significant figure. If we have 205.0, so right now you see that this is a trapped 0 because it is between 2 non-zero values, and this 0 is a trailing 0 but coming after a decimal point, so we have 4 significant figures in it, right? Similarly, if we have, let's say, 2.050, so again this 0 is between 2 non-zero values 2 and 5, and this is a trailing 0 which is coming after a decimal point, so it will be counted. So we have 1, 2, 3, 4, again the 4 significant figures will be there, right? So I believe the idea is very, very clear. So if we have a trapped 0, it will always be a significant figure, right? If we have a trailing 0, then we have to look for the decimal point, right? What about the leading zeros? Leading zeros are never going to be significant. So here the zeros are there and there is no non-zero number before that. So leading zeros are never significant. Never significant figures, right? So basically these zeros will not be counted. For example, if we take another example, right? If we have 0.025, so this 0 is a leading 0. Only these two are non-zero things. So we have 2 significant figure. 0.0205. So in this one, we have this is trapped 0 and this is leading 0. So we'll not be counting. So 1, 2, 3, we have 3 significant figure. 0.02050. So here you see that this is a leading 0, will not be counting as a significant figure. This is trapped and this is trailing 0, which is coming after a decimal point. So it will be counted. So we have 1, 2, 3, 4, 4 significant figures, right? So the idea is very clear. Once you know the what kind of 0 you are dealing with, you can easily tell that what will be the whether or not you will be counting that as a significant figure or not, right? So this is the entire idea, right? This is all the rule you need to keep in the mind, considering when a number should be counted as significant and under which circumstances you will not be counting a number as significant, right? So for non-zero it is very clear, and for the zeros it is very clear. Now let us talk about the powers of 10. Again, it is also very simple. When we are talking about the powers of 10, we don't talk about the significant figures in this section where the 10 to the power something is written. We will only talk about the significant figures over here. So here we have two significant figures. All of them are non-zero numbers, and non-zero numbers are always significant. So here you can talk about that we have how many significant figures? We have two significant figures, right? 1.70, there is a decimal point, and after that we have this 0 over here. So here we will have three significant figures. 170, right? So here we don't have a decimal point, and this is a trailing 0. So here we will have only these two digits as significant digits, right? 1.70700. So right now you see that there is a decimal point and then there are trailing zeros. So they will be counted as significant. This one is trapped 0. This one will be counted as significant. So we have 1, 2, 3, 4, 5, 6, 7. We have in this digit, how many significant figures we have? We have 7 significant figures. I believe the idea is very, very clear. This is the entire idea behind it, right? How many significant figures we are going to have in the powers of 10. Let's talk about the exact measurement. Again, when we talk about the exact measurement, for example, we have, let's say, one scale, we have another scale, and we have another scale. So how many scales I have? 3. So I can write down the number of scales I have over here is 3, right? The number of scales I have over here is 3. So number of scales I have is 3. I can write down as 3, 3.0, 3.000, 3.0000000, right? So if I write it like 3.0, I have 3.0 scales over here. How many scales I have on the in front of me? So we can just put it 3.0 scales I have. And I can say that there are two significant figures over here, right? I can say these are the number of scales I have. I can say these are the number of scales I have. If something is a exact numbers, we will say that it can have infinite number of significant figures. For example, let's say I have 12 apples, right? I have 70 books, right? So all these exact measurements are considered to have infinite significant figures, right? So exact measurements have undefined or infinite significant figures, right? Exact measurements have infinite significant figures. And why we learn about that? Because in the case of algebraic calculations, we don't consider the significant figures attached with the exact numbers, right? So we will talk more about that in the algebraic part. Let's move on and talk about the next idea, rules for rounding off. My dear students, after learning this concept, right, what will happen? There are certain calculations in physics, right? Sometimes a question like that is asked in the paper as well. Like if I want to add, let's say 1.7 to 1.070215, right? Look for that. Here we have only one thing after decimal, and here we have so many things after decimal place, right? So if we have to add them up, we cannot do that, right, without converting the other part to the two decimal places, right? Like to the two significant figures, right? So over here you see that you have to first remove few numbers from it, right? And then you can add. While you are removing something from it, basically you are changing this value to its approximately closest value, right? So this is the algebraic calculations you are doing, right? And how to do that? This is the process of you called as rounding off, right? When you drop a certain section, right, to keep the value till a certain decimal places, this is called as rounding off. For example, this is what we do at departmental stores all the time. Let's say the total value that you have to give comes out to be 53 rupees and 20 paisa, right? Then he removes that 20 paisa, right? He rounds off that 53 rupees is something that you have to give, right? But if it is 53 rupees and 90 paisa, then he will say that give me 54 rupees, right? So just like that, we have to round off something to the given value. So how do we do that? Let's have a look at that. How do we round off, right? And this rounding off comes very, it becomes very useful in very so many situations. So here you have, we have to round off this thing, let's say up to two significant figures. We have the first value 1.275 and we want to round off at two significant figures. So this is going to be significant, this is going to be significant, and this remaining portion we have to remove. Okay. Similarly, let's say that we also want to round off to two significant figures, so we have to remove this part, right? So whatever the last remaining digit is, let us give that digit as a name, right? Let's call that one as cutoff digit. Let's call that digit as a cutoff digit, and the remaining portion after the cutoff digit is cut off, yani removed. All right. So we have 1.2. So after that, this 2 is the cutoff digit, and after that, the portion is removed, right? So see that the rule is very simple for the rounding off. If the value after the cutoff digit is more than 5, right, then the cutoff digit is increased by 1. So right now, what will happen while rounding off, the value that you are removing, the digit that is coming after, right after the cutoff digit, is more than 5. So we will increase the value of cutoff digit by 1. So 2 we will increase by 1, it will become 1.3, right? And the value that is coming after the cutoff digit is 4, which is less than 5. So we will not change it. So we will keep that value as it is. This is simple, right? If the value of the cutoff digit is more than 5, increase the cutoff digit by 1. If it is less than 5, keep it as it is, right? No problem in that part. No problem in that part at all. But what will happen if the value after the cutoff digit is exactly 5? Let us say that in this example as well, we want to, let's say, keep only two significant figures. So we want to remove this section, right? And how to do that? Because the value after the cutoff digit is 5 in both the cases. So in this situation, we have a standard rule that is common across all the books. Let me tell you straight right away. Right. So it's a convention what we do. If the value after the cutoff digit is exactly 5, neither more than 5 nor less than 5, then we look for the value of cutoff digit itself. Then we look for the value of this digit itself. If the value is even, which is the case over here, if the cutoff digit is even, then we make no changes. Right, so 1.2, 2 is even, so we will say that the final value is going to be 1.2. So this remaining portion can be removed without changing the cutoff digit. Neither we will increase it nor we will decrease it. But if it is odd, you see that here we have the portion that is removed has 5. So neither more than 5, less than 5, it's exactly 5. So we will look for the cutoff digit. It is odd now, right? And if it is odd, we will increase by 1. So the value will become 1.4. So I believe the idea is very clear, right? What will happen in a certain circumstance? This is the rules for rounding off, right? So now let us move on and talk about how to apply these rules. This is the simple rule, right? Now let us talk about the rules for rounding off, right? And apply those concepts when we are doing the algebraic calculations in the case of significant figures. So here we have it. We have addition or subtraction going on for us, right? We have these values at us 1.6, 1.78, 1.3250, right? And we want to add them up, right? So how can you do that? So we can say the number of significant figures in all of these calculations is different, right? So what can you do? So here you have two significant figures, here you have 3, and here you have 1, 2, 3, 4, 5. This 0 is trailing 0, right? And it's coming after decimal point. It will be significant. So in the case of addition or subtraction, we must consider the value with the least number of significant figures. So here this one has least number of significant figures. It has only 2. So we have to convert the remaining as well up to 2 decimal places, right? So it has 2 significant figures. We have to keep this one as well till 2 decimal places. So 1.7, we have to remove this part. It will become cutoff digit 7, right? But the value after the cutoff digit is more than 5, so we will increase it, right? So here we will have 1.7, we will become 1.8, right? I believe the idea is very, very clear. Okay. Over here, you see that 1.3250, we have to keep this one as well till two decimal places, till two significant figures. So we have 250. The value after the cutoff digit is less than 5. We will not make any change. So this value will remain 1.3, right? So just add them up now. It is 1.6 plus 1.8 plus 1.3. This is what you need to add, right? And this is what we will give you the answer, right? That's it. Now, in the case of multiplication or division, in the case of addition or subtraction, you go with the least number of significant figures and you add it, right? Or subtract it, right? In case of multiplication or division, what you do? Again, you do the similar thing, right? You consider the least number of significant figures with a little bit of catches over here, right? You have 1.2 into this. So this one has two significant figures and this one has 2 and 3, 5 significant figures. The result cannot have more than the least number of significant figures. We have to talk about this one. We have 2. So we will keep only 2 significant figures at the end. Right. So the result has right now so many. So we have to drop this portion off. Right. But the portion which is dropped off, the portion that is dropped off is more than 5. The value after the cutoff digit is more than 5. So we will sum it up. We will round off that by increasing the cutoff digit by 1. So this will become our answer. Right? Over here you look at that 1.2, it has two significant figures, and over here we have 1, 2, 3, 4, 5, 6, 6 significant figures. So answer should have only 2. But my dear students, many kids get confused in this example. So it's a very good example. Right. So look at that 533.678. Right. So if I drop it till two significant figures, the answer will be only 53 something. Right. But that will be wrong, right? If you are multiplying something and the answer is more than 500, and while rounding off, you cannot make it 10 times lesser. It feels wrong, right? So in this situation, what happens? We don't go about that, right? Okay, we don't go like that. 533 point this. So how do we go about in this situation? Let's talk about that. So here, first of all, convert the whole thing into 10 raised to the power, right? Into 10 raised to the power. So you can write down like that. So decimal place can be taken over here and you can write down as 10 to the power 2 like this, right? So here right now, we don't talk about the significant figures of 10 raised to the power part, right? We know that. And we only have to keep two decimal places, right? Two significant figures, sorry. So two significant figures, this one and this one. Rest part you have to round off, right? And you see that the part after the cutoff digit is less than 5. So we will not change it. So we will keep it as it is 5.3 into 10 raised to the power 2. So or we can say it is 5300 like that. So right now you see that in this value we have only two significant figures. That was a desired value, right? These trailing zeros will not be significant. You can keep it in this way or this way. In both cases, you have only two significant figures, which is our desired result, right? So if in the NEET paper, they are giving you multiply this and this, right? And they are giving you different options. What should be the correct representation and what should be the number of significant figures in the result? Many kids might get confused that if they multiply this, you will get a value which is more than 500. All the non-zeros are going to be significant, so they will count all of them and they'll give the wrong answer that they are going to have 6 significant figures in the result, which is going to be wrong, right? In the case of multiplication as well, you are going to consider the least number of significant figures, and to do so, you can use this method where you can raise the final value to 10 raised to the power and consider the least number of significant figures. I believe the idea is very, very clear. Now, let us talk about accuracy and precision. So, many books are defining these terms in a very detailed fashion, but that is not needed at all, right? Let's talk about the least confusing way to understand what is accuracy and what is precision, right? Now understand that clearly I have these instruments, just to measure the length, right? So I can measure the length with this one. I can measure the length with this Vernier caliper, and I can also measure the length with the help of this scale, right? All these instruments will help me to do the same things, just to help me to measure the length of an object, right? Now let us say that I had a box, I had a new object, and the length of this object was written behind it, right? The length of this object was written right behind it, okay? Let's say that true value was written as 5.0, right? Let's say 5.0 centimeter, okay? And I measured it with all the instruments. Some instruments were more detailed, right? They could measure up to 2 decimal places. Some instruments were less detailed. They could only measure up to 1 decimal places. And some instruments were like this, right? For example, this measuring scale. So over here, you will not find a centimeter mark, right? In this one, I do not have a centimeter mark like this. So in this one as well, we cannot, because the final value is in centimeter, so we will not have decimal places in that situation. So like that, we can measure it, the measured value. These are the measured values with different instruments, right? So one instrument is measuring it 4.875, right? Second instrument is measuring it 4.9. Third instrument is measuring it 5. All right. So now out of all three, right, or let's make only 2 measurements for now. Out of these 2 measurements, which is going to be more accurate and which is going to be less accurate? Okay, let's first talk about that. If we are talking about accuracy, and here you have seen that we have taken 2 measurements with different measuring instruments. One could give me 3 values after decimal place, and one could measure only after 1 decimal place. All of them are in centimeter, right? All of them are in centimeter, right? So my dear students, the true value was 5.0. And you see that there are 2 measurements. Even if the first instrument can measure up to 3 decimal places, it is slightly further away from the actual value, right? It is 4.8 something, right? And here we have 4.9. This is much closer to the true value. So we can say the instrument which is closer to the true value is more accurate, right? So what is the meaning of accuracy? How close you get to the true value of any measurement, that gives you the accurate value, right? So here you are, this is going to be more accurate. All right, this is going to be more accurate. What about the first one, 4.875? Here, this instrument has more detailed view, right? And if you are going to measure it again, it will again measure up to 3 decimal places, right? So the preciseness is about the detailedness in the measurement, right? So the instrument that can measure up to more decimal places will be considered as more precise instrument, right? So think about it. The second one can only measure up to 1 decimal place, while the first one can measure up to 3 decimal places. So here, this is more detailed measurement. So this is going to be more precise measurement. All right. So you see that this is precise but not that accurate. This is more accurate but less precise. The ideal case would be we are precise as well as accurate. This is going to be the ideal case, but right now we have these observations with us, right? Here the first observation is more precise but less accurate, and the second observation is more accurate but less precise, right? So accuracy has to do with how close the given measured value is to the true value, and precision is about how detailed the measured value is, right? So this is it. Let's look at this question. It was asked in one of the previous years. So the question is asking, the mean length of an object is 5 centimeter. This is the mean length. You know that the mean length or the true length, true value, mean value or true value are the same things. So the mean length of an object is 5 centimeter. Which of the following measurements is most accurate, right? So most accurate. So when we talk about the accuracy, are we dealing with the decimal places or are we dealing with the closeness from the true value? True value was 5. So look at that. We have 4.9, only slightly away from 5. We have 5.25, further away from 5, even if we have more detailed value, 2 decimal places. So we will say that it is less accurate. This is more accurate. What about this one? 4.825 and 4.9. 4.9 is closer to 5 than 4.8 something, right? So even if it is more precise, it is less accurate, right? It is less because it is not closer as compared to this one. 5.4, so further away from it. So again, not accurate, right? So here we have this one as most accurate measurement. So the correct answer would be 4.9 centimeter. This is the most accurate measurement in this given situation, right? So I hope the idea is very, very clear about the significant figure and about the accuracy and precision, right? So this is pretty much everything about this specific concept. Now let us start talking about the next one, which is the basic mathematics, right? So without any further delay, let us start talking about the concepts of basic mathematics, right? So now let us start understanding the concepts of basic mathematics. Now, as far as the maths goes, sometimes we get confused that why we are getting maths in biology, right? Like we are PCB kids mostly. Then why are we going ahead with mathematics? My dear students, understand that going ahead when we are going to work with the kinematics and all, right? There are going to be certain applications of basic mathematics that if you are not very clear with, then there will be serious problems. So my dear aspirants, I'm not going to teach you a lot of mathematics over here, right? We are not going to dive deep into calculus and dealing with product formulas and all those things. We just need basic. And why are we doing that? Just we need basic intuition, right, of mostly calculus, right? If you are clear with just that, we can understand kinematics and rest of the things really well. And the calculus or the rest of the mathematics will not be a hurdle to us, mostly calculus, right? Let's understand the significance of few things. So this is a basic sign convention thing, right? You know that in a case of trigonometrical calculations, we follow a quadrant, and this is ASTC. This is the basic 10th level mathematics, right? So in the first quadrant, everything is positive. All the trigonometric ratios are positive. In the second quadrant, what happens? Sine and cosec are positive. Then the third one, tan and cot are positive. And the fourth one, cos and sec are positive. So ASTC you call it, right? Some people call it all student ticket collector. So whatever that you used in that grade 10th. Now this is the main idea, basic meaning of differentiation and integration, right? So let's start talking about that. So why do we differentiate? The question is why? Sir, can't we understand physics without differentiation and without integration? So the answer is a very hard no, right? So understand that when we are going to start talking about the kinematics, in the very basic principles of kinematics, differentiation will help us, right? It's a very interesting tool, right? If you focus on this one, let's say for 1 hour or 2 hour, understanding rest of the physics will be very, very easy for you, right? So over here, right, like right now I'll just tell you for a few minutes, but the formulas that you have to remember, that will take 1 or 2 hours, I'm saying, right? For differentiation is, why are we doing the differentiation part? Differentiation tells us two things: rate of change of something, or it can tell us, not always, but it can tell us, or if we have the graph between two things, it will tell us about the slope. It will tell us about the slope. About the slope, right? So it can tell us about the rate of change of something, and it will tell us about the slope of something. For example, what do you mean by that? Understand that. So let's say that anything is written, like there is a thing called y, there is a function called y, right? It's a function of x, right? And what is happening? Let's say that a particle is moving in x direction, right? And what is happening? Its velocity is changing, for example, right? Right now the particle is moving slowly, then it is moving faster and even faster, then even faster, like that, right? So particle speeds up, so its velocity is changing with time. This will be a better way of saying it. Let's say we have a particle with a velocity which is a function of time. Velocity is a function of time. If that is happening, velocity is a function of time. That means velocity is changing with time. Then what will happen if I try and do this thing, dv by dt, differentiation of velocity with time? This expression tells us how quickly the velocity changes with respect to time. dv by dt tells us how quickly the velocity changes with respect to time, right? Or we can say rate of change of velocity. Change of velocity. All right. So differentiation can help us find out rate of change of something, right? Rate of change means if something is calculated with respect to time, or it can also help us figure out the slope of something, right? So for example, if I have a graph between x and y like this, we have x-axis, we have y-axis, we have a graph like this, right? And at this point, if I find the differentiation, the value of differentiation, then it will tell you dy by dx will tell you the value of dy by dx over here, will tell you the slope over this place, right? Okay, so idea I believe is very clear. So this dy by dx, the differentiation helps us in two situations. When you want to find out the slope at a certain place, in some places we will do that, and in some places we have to find the rate of change of something. In that cases, differentiation helps us. This is the basic thing. If you just keep that in your mind, your function, your purpose with differentiation is mostly solved. So these are the basic formulas, right? And this is how you differentiate that. If y is a constant, right, then differentiation of y is 0. If y is x to the power n, then differentiation of x to the power n is nx to the power n minus 1. If y is representing sin x, differentiation of sin x going to be cos x. If y is representing cos x, differentiation of cos x will be minus sin x. If y is representing tan x, differentiation of tan x is sec square x. Y is representing e to the power x, its differentiation is again e to the power x. If it is ln x, then it is 1 upon x. Differentiation is 1 upon x. So these are the basic formulas. You have to keep these basic formulas in your mind, right? And now let's talk about the integration. What is the physical significance of integration? Why do we need to integrate in physics, right? So understand that. One way to understand integration is it lets you go back, right, from whatever differentiation you just got, right? You can go back to the previous step, but that's not a physical significance. What is the physical significance of that? Integration helps you to find out the area under the curve, right? What will you get? Area under the curve. Right from the kinematics, this differentiation and integration will start helping us. So integration helps us to find the area under the curve. All right. For example, if I have this little graph like this between, let's say, velocity and time, all right, this is the graph of velocity and time. This is one value of time t1 and this is another value of time t2. From t1 to t2, if I take this area under the curve, right, how will I get that? So this is going to be integral of v dt from t1 to t2. This is the area under the curve. This is the Vt graph, right? So this is integral of V dt from where? T1 till where? T2. This is representing the area under the curve of Vt graph, right? Integral, T1 to T2 V dt, right? And it will help you to figure out few very interesting things. And what are those interesting things? That I'll tell you in kinematics and all, right? So these area under the curve in some cases represent a meaningful physical quantity. Not always, but in some cases this area under the curve represents a meaningful physical quantity, right? And since we don't know the integration, since we don't know what this term represents, we start hating the maths altogether, right? You will find that it is going to be very commonly intuitive that we are using this expression, and this expression is nothing but area under the curve, area under the Vt curve from T1 to T2, right? And this expression is telling us something. What does that tell us? That it is telling us area under Vt curve from T1 to T2, right? Area under the Vt curve from T1 to T2. And in physics, this might tell us a physical quantity, right? What is that? We will talk about it later. right? So definite integral, it will tell us about the area under the curve under certain limits. And these are the formulas, right? For integration, if we are integrating 0, we will get a constant. If we are integrating 1, we will get x plus c, right? So if you are integrating 1, we will get a constant, right? Integrating x to the power n, we will have x to the power n plus 1 upon n plus 1. Integrating e to the power x, we have e to the power x plus c. Just like that, we have the entire list over here, right? We have the entire list over here, right? So I believe the ideas are very, very clear, right? Okay. Alright, so these are again the common set of formulas. A plus b ka whole square is a square plus b square plus 2ab. A minus b square is a square plus b square minus 2b. So these are the basic formulas, right? You have to keep these formulas as well. This is in the basic algebraic calculations, sometimes they might come in handy, right? And these are some logarithmic constants. So ln x is log x base e is 2.718, 1 upon e is this. These are the basic things. If you keep them in your mind, it will always be easier on the calculation front, right? And this is again some properties of log. If you multiply the log and take the log, then what will happen? It will distribute over the entire thing. And if you divide it, then it will distribute like this in the entire thing, right? So these are the properties of log. These are the basic exponents. So if you have the same base, power is x and y, the powers will be added up, right? So division rule, if base is same, powers are different, then powers will be subtracted. Again, the basic same rule, right? And that's pretty much everything, right? These are the basic simple mathematical tools you need to have in your mind so that you can simplify the calculations. So you can understand when we are using certain mathematical calculation, right? This is pretty much everything, right? I hope you have understood each and every concept of this particular lecture, and the concepts of units and measurement is clear to you. And at the end of it, I have also given you a brief about the mathematical tools that you are going to get in, that you'll be using in upcoming lectures and upcoming chapters, right? On that note, just download the DPP from the description box, right? Solve it, and I believe most of the questions you should be able to solve by yourself, right? So just go ahead and download the DPP, and this is your turn where you can solve it. All right. So this is it for now. I'll see you there in the next class.